Hello everyone, welcome to the 14th lecture in this series. With this lecture, we are going to explore some of the applications of Stack. Not only with this lecture, but with the next lecture also, we are going to study some of the applications of Stack. But in this lecture, to be specific, we are going to explore more on recursion and how stacks are getting employed to handle recursive functions, and specifically we will be focusing our attention to the towers of Hanoi problem, where how stack finds its use. Let us first see what recursion is. Recursion is basically the process by which a function calls itself again and again. So, recursion can be of many forms. Say in the first case, we assume that we have a function named x, and the function x calls itself again and again. This is one way of dealing with recursion, and otherwise recursion could also be cyclically or go in the way of a chain. So, imagine that we have functions named x and y, where the function named x would make a call to function y, and the function y will again make a call to x. So, here you could see that the calls to the function x and y happen in a cyclic fashion. So, in both ways we can see that ultimately a function calls itself. So, that is what we mean as recursion. So, we normally use recursion whenever we want to have some repetitive computations. So, there are certain conditions which need to be true for recursion to happen. One is that every action should be capable of being represented in terms of result to a previous step. So, in case let us consider factorial as a function. So, if I want to have the factorial of n to be computed, then factorial of n should be represented in such a way that its solution is relying on some of the previous step. So, fact of n is nothing but n star fact of n minus 1. So, if I want to compute the factorial of 5, we know that it is 5 into fact of 4, right. So, if I am able to express the solution as some of the previous step, then we can very well represent the function in a recursive way. So, these are the conditions which need to be true for a problem to be written in a recursive form. So, first is that it should be possible to express the problem solution in terms of solution of the same problem, but on a small sized data. So, that is what I said before. If I want to find the factorial of 5, I should express the solution for factorial of 5 in terms of its smallest sized data, that is fact of 4 in that case, right. So, that is the first condition that has to be true for a problem to be written in a recursive form. The second criterion that is expected is the problem should contain a stopping condition. So, when we frame the problem statement, it should have a stopping condition. So, in the case we consider factorial as the problem, then the stopping criterion there would be like when n is 0, factorial of 0 is 1, that is the stopping criterion. So, for all other values of n, we always say that fact of n is n star fact of n minus 1. So, that is what we say as the recursive form or recursive definition. So, if suppose a problem is capable of being expressed in a way that its solution is always a result of some smaller step in the problem, or and that too in addition, if the problem statement has a stopping condition, then we can very well express that problem in a recursive fashion. So, here in this slide we see some of the example problems that are handled in a recursive form. The second example you see here is the computation of GCD of two numbers. You know, when we want to find the GCD of two numbers, if both the numbers are same, then the GCD is going to be the same number. If m and n are two different numbers, we find m mod n, and if suppose m is greater than n, we compute the GCD of m mod n and n, and if it is m is less than n, we compute the GCD of n and n mod m. So here we are able to have a stopping criterion, as well as we are capable of expressing it in terms of some smaller steps. Let us consider the next example where we have the Fibonacci sequence. A Fibonacci sequence is one in which the first term is 1, the second term is also 1, and the third term is actually the sum of the first two numbers, that is 1 plus 1 is 2, and the fourth term in the sequence is the sum of second and third numbers, which is 1 plus 2, which is 3, and the sequence goes that way. So here the thing that is fixed is the first and the second terms in the sequence, that is fib of 0 and fib of 1. So that too can be considered as the stopping criterion there. And other than that, for all other values of n, always it is the sum of the previous two numbers in the sequence. So if I say fib of n, then it should be the sum of fib of n minus 1 and fib of n minus 2. So that is why we have expressed that problem statement in a recursive form at last. So the first two lines become the stopping condition, and the last line becomes the recursive definition for Fibonacci sequence. So here you could see how recursion actually works, considering factorial as the example. So here first let us see the function for factorial. We have a function named fact that takes in integer value n and returns a long integer, and the function definition goes this way: if n is equal to 1, then we return a value of 1. So here in our case, that is the stopping condition. Otherwise, for all other values of n, we make a recursive call to the function as n star fact of n minus 1. So n would be constant, and fact of n minus 1 is the recursive call to the function. So let us consider this function with 4 as the input. So let us see how this actually evaluates. So we make a call to the function with value for n as 4. So it is fact of 4. So initially the function expansion happens this way. We check whether 4 is equivalent to 1, and it is false. So we return fact star fact of n star fact of n minus 1. So in our case, our n is 4. So 4 star fact of n minus 1, which is 3. Now there is a recursive call to the function named fact, but here now the argument is 3. So again we make a check whether 3 is equal to 1. In our case this is false. So we do process the else part, which is return of 3 star fact of 2. So here what we need to observe is that this function has not returned a result. As of now, the computation is pending. So this is where stack gets applied here. So whenever some computation is left pending, in that case those statements would be actually stacked up in a stack. So as such, this function has not returned a value successfully, rather it would stack the value 4 star fact of 3 in a stack. So in the next case we have 3 star fact of 2. So in that case also the function cannot return anything, just because the computation is not complete at this moment. So this should also be pushed onto a stack. So now there is a call to the function fact with the 2 as argument. So once again call to function fact will be made. So now we come across this statement, we check whether 2 is equal to 1. It is false. So we move to the else part. There we have the statement 2 star fact of 1. So now also the function cannot return, just because computation is incomplete. So we push this statement also onto stack, and at last we make a call to the function named fact with 1 as the argument. Now we check whether 1 is equal to 1. Now the condition is true. So we return a value of 1. So now we have got the result for fact of 1, which is 1. So that is being returned to the value at the top of stack, which is 2 star fact of 1. So in place of fact of 1, the value of 1 gets substituted. So we compute 2 into 1, which is 2. Now the function can return that as the result. So this result has to be returned to this function fact of 2. So we return the value of 2 to fact of 2. So, fact of 2 now gets a value of 2. So, we multiply 3 into 2. So, we have 6 and that has to be returned to the function fact of 3. So, 3 has a value of 6 now, and so we compute 6 star 4, which is 24, and that is result as returned as result for fact of 4. So, ultimately when I make a call to this function with the value of 4, this function would return me a value of 24, and of course, the computation of 24 is not straightforward. It has involved recursive functions within it, and so we indirectly make use of stack to hold the intermediate pending computations. So, here in this example I have just shown of this same code for factorial computation. I have just showed the results of execution of this factorial function. So, here you have a main function, we get a value for x, and we make a call to the function named fact with x as the argument, and whatever function fact returns, that is captured by y, and finally we print that as the result. And we have the definition for the function named fact. It takes x as the argument. In place of x we have data here. So, within the fact function, just to for the sake of demonstration, we just print the values for data, the address for the variable named data, and we also print the value for print the address for the variable named value. So, initially value has a initially we have declared a variable named val with value as 1, right. So, here you could see if data is greater than 1, then we call this function. So, we have the statement value is equal to data star fact of data minus 1. So, otherwise, so here this is our actual expansion or recursive definition here. So, we have the recursive definition here. Just for understanding sake, we have put up a printf statement before this recursive definition to know the intermediate values during execution. So, initially as you see, I make a call to the function with the value of 4. We have a call to the function fact with the value for data as 4. So, that is why data has a value of 4, and you could see the value for I mean the address for data, some memory address there, and you could see the address for the variable val, that is also some other address, memory address. And every time you see the value for memory address for data as well as for value is not the same, it keeps on changing, which means the address for these variables are assigned at the time of execution. So, that is these addresses are actually available at the program's heap. So, hope you remember what I said during one of the earlier lectures, that whenever a program is put to execution, you know the program is now available in memory. Not only the program, together with the program, the data as well as some portion of memory is reserved for heap, and the portion of memory reserved for heap is meant for dynamic memory allocation as well as for the purpose of storing stack. So, whenever function calls are made, you know, in order to preserve details associated with the function, we have to maintain an activation record. Of course, I will be explaining in the further slides what activation record is. So, in order to hold those activation records as well as all the variables associated with it, we have space in the heap. So, here the addresses actually correspond, the addresses are all different, and these addresses are assigned at the time of recursive calls to the function named fact. So, the purpose here is that you could see the addresses are all different, and you could see that the function fact has been invoked 4 times with different values, and ultimately as we saw before, the value for factorial of 4 is 24, and that is being returned by this function. And let us now consider the other example, which is Fibonacci sequence. As I said before, in a Fibonacci sequence, the first 2 terms are 1. So, when n is 0 as well as n is 1, fib of n should return a value of 1. For all other values of n, fib of n is going to be fib of n minus 2 plus fib of n minus 1. So, this is the problem statement. So, here as I said before, we should have a stopping criterion or a base, and that is what we have for n equal to 0 or n equal to 1. It is going to return 1, and this is the recursive definition. For all other values of n, fib of n is going to be fib of n minus 2 plus fib of n minus 1. So, that is what we have shown here. Now, let us see how this Fibonacci sequence is actually working for some specific input. So, we understand this definition for this function fib. It is actually the exact implementation of what we have said with the problem statement for Fibonacci sequence. So, for n is equal to 0 and 1, it returns 1. For all other values, it returns fib of n minus 2 plus fib of n minus 1. Now, let us consider that we invoke this function with fib of 5. So, initially we check whether our n is 0 or 1. It is not the case. So, we have to return fib of n minus 2 plus fib of n minus 1. So, in our case n minus 2 is 5 minus 2, which is fib of 3, n minus 1 is fib of 5 minus 1, which is 4. So, we have fib of 3 plus fib of 4. So, here we have two recursive calls to that function, one with fib of 3 and another one is fib of 4. So, now let us consider the left side of this tree. So, fib of 3 has to again we make a call to this function. We check whether 3 is 0 or 3 is 1. It is false. So, it should be 3 minus 2 and 3 minus 1. So, 3 minus 1 is 2, 3 minus 2 is 1. So, it is fib of 1 plus fib of 2. Now, as you know, we have the value for, we have to again invoke with fib of 1. So, fib of 1 is 1. So, it returns a value, whereas fib of 3's computation is pending, fib of 5's computation is also pending, and now we are in fib of 2. So, when I make a call to the function with fib of 2, then it will return fib of it is fib of 0 plus fib of 1, and of course, this is the base condition. So, we know fib of 0 is 1 and fib of 1 is 1. So, it returns, and these two values are returned to fib of 2. Only with that, by summing up this 1 and 1, fib of 2's value is got, which is 2, right. So, only when fib of 2 is ready, we can compute the value for fib of 3, which is sum of fib of 1 plus fib of 2. So, we sum up 1 plus 2 and get 3. So, now we have computed the left half of the tree. Similarly, we may have to do for the right side, where we have fib of 4, which is expanded as 2 plus 3, and 2 will be expanded as 0 and 1, 3 will be expanded as 1 and 2, and 0 and 1 will be straightforwardly returning 1 and 1 as an result, and whereas fib of 2 has to be again expanded as 0 and 1, and finally, we get the value for 0 and 1 as 1 and 1. So, once this is done, I will be able to get the result for fib of 2, right. Once fib of 2's result is obtained, then we may be able to substitute the answers for fib of 1 and 2 and return the result as 3 for fib of 3. And once fib of 3 is ready, then we may be able to compute the value for fib of 4, which is sum of this and this, that is 2 plus 3, which is 5. And finally, only when we complete the entire right subtree, then we may be able to compute the value for fib of 5, which is 3 plus 5, and the solution is 8. So, you can see that merely invoking for fib of 5 has ultimately made us to call fib of function several times, as you see here, and in some cases we end up with the base condition, and some other cases that again has made us to make a recursive call to that function named fib. So, now let us see how function calls are actually implemented. So, as I said, whenever a program is running, there will be a portion of memory reserved for stack, and already we have learnt the data structure stack. It is a last in first out list, and we learnt how to do push and pop operations on it. So, whenever a function call is made, an associated activation record is getting pushed onto the stack. An activation record is one that holds the value of the return address. So, you know, from the point where a function call is made, the control jumps to the function definition, corresponding function definition, and once the function definition gets executed, the control again has to branch back to the place where I mean to the next position from where the call was made initially, right. So, the return address has to be preserved somewhere. It is in this activation record we preserve this return address. Not only that, at the time of making a call and the control being jumped to the place of function definition, we may be dealing with many variables in the actual program from where a call was made. So, such value should also be preserved somewhere, and in the activation record we do actually maintain or preserve all those values. So, the local variables inside the function will get stored in that function, and the return value from the function will also be preserved in the activation record. So, activation record is very important with respect to implementing function calls, and in order to handle all those activation records, we usually use a stack. So, whenever we call a function, we push the activation record onto a stack, and whenever we return from a function, we pop up the corresponding activation record and resume execution with the main function, right. So, this is the very purpose of having a stack to hold activation records in order to implement function calls. So, the same has been demonstrated with an example. Here you could see we have a main function. Within the main function, we have a call to the function named GCD with two arguments a and b. And so, here you could see that we have some statements above this function call, and at times they may involve some variables and some other computations, and all those are actually preserved in the activation record. And not only that, we also have the return value as well as return address being preserved in the activation record. So, this is how the status of stack would look like. So, at the time before the call, you could see that this is the content of stack, and as soon as function call is made, you could see that an activation record is being pushed onto the stack, and once we return from the called function and resume execution with our main program, then the program execution would resume by fetching the return address and all the return values and the local variables from the activation record, and then normal execution of the program would resume in main. So, this would be the status of stack after the activation record being popped from the stack. So, this actually explains what happens during recursive calls. So, I was telling you before how activation records work with respect to function calls during a normal function execution, and in terms of recursive calls, it means we make a call to the function again and again. So, every time a function call is made, a corresponding activation record would be generated, and that has to be pushed into the stack. So, in terms of recursive functions, more and more of activation records for the same function will get created and will be pushed onto stack. And when we return from the function, when we return from a particular recursive function, the particular activation record will be popped off from the stack. So, in a recursive function, a function calls itself. So, we know very well that here in this case, in case of recursive function, we may not be returning the result straightforwardly. At times the results will be will rely on results of previous step, and in such a case the activation records may have to remain in stack for a long time till the previous step returns the result. So, more and more of activation records will get pushed into the stack continuously. So, whenever we deal with recursive functions, we are supposed to have a large stack space. Only then we may be able to accommodate more number of activation records as more and more of recursive calls are made to the same function. And whenever a recursive function returns a value, at that moment activation record will get popped off from the stack. So the stack would become empty only if the termination condition of the recursive function is reached. So here in this example we are going to see how stacks are used to handle activation records when recursive calls are made. So here we have a main program from where we make a call to the function named fact, and we are going to call this function fact with the value of n as 3. So this is going to be the definition for factorial function, and you know very well how this activation record will look like. It will have all the local variables in that function maintained. So in our case the local variable is n at this moment, and it will have all the return values, and it will have the return address as well. So this is how your activation record will look like. So now we are going to see the trace of the stack during the execution of factorial function with the value of n equal to 3. So initially from the main we make a call to the factorial function with the value of n is equal to 3. So when a call to this function is made from main, then we may have to create an activation record for main, where we have to preserve the return address. There is no return value at this moment, and so it is put as hyphen here, and there is only one local variable in main function, which is n with the value of 3. So that is what we shown here. So when I make a call to factorial with n is equal to 3, so as by definition we understand only for n equal to 0 it returns 1. For all other values it returns n star fact of n minus 1, right. So now again we make a call to the function with the value of n as 2, fact of n is equal to 2. So now the local variable there is n is equal to 2, there is no return value, but the return address is that factorial functions, just because now the call to factorial function is made from fact. So we have the return address as fact. Earlier the return address was main, just because the call to the function was made from main. So when I make a call to fact of n equal to 2, that is again expanded as 2 star fact of n minus 1, right. So there is going to this is going to generate one more activation record for us with n as 1, and return address will be the same factorial function. And when I make a call with fact of n as 1, again it creates an activation record with the fact of n equal to 0, right, and that is the activation record there. And so whenever a call is made, the corresponding activation record has to be pushed onto stack, and that is what we have shown here. But n equal to 0 is a base condition for which there is a return value. The return value is 1, that is what being substituted here. And very well the call was made from factorial function, and so the return address is the factorial function itself. So now as this function is returning, now this activation record will be popped from the stack, and this return value has to be substituted to will be returned to this fact function. Just because the return address is fact function, this value is returned to this place. So we compute 1 star fact of 0. So 1 into fact of 0 is 1, that is the value returned from there. So that is computed here. So now we have a value of 1. So now this value has to be returned to the fact function. So I return it here. So we have the next activation record about to get popped off once this computation is over. So now we have the value as 2, and this value can be returned to the factorial function here. So that is returned. So activation record will be popped off, and finally the value returned to main is nothing but computed as 3 into 2 6, that is returned to main, right. So this is how the stack is employed at the time of making a recursive call, you could see that during every recursive call a corresponding activation record being pushed on to stack, and once computation gets done, now the function has to return the value. So, whenever a function is returning, the corresponding activation record being popped up and the corresponding value is being returned to the said return address. And that is how you could see that once the activation records were stacked up, and finally once values are computed, the activation records are being popped off and final value is returned to main. Now, we are going to see how this stacks and the concept of recursion can be applied to the problem of towers of Hanoi. So, it is actually a puzzle, an interesting puzzle. So, the problem goes this way: we are having 3 poles and we have some disks put on the poles, and you could see that all those disks are of various varying dimensions, and they are stacked in such a way that the one below is larger than the one above, right. So, this is the arrangement of disks on the pole, and our objective is that we have to shift all these disks from left to the rightmost pole, and we have some intermediary pole where we could hold this disks in between during shifting from left to right. But at all times we need to ensure that the disks are in such a way that the one bigger is at the bottom and the one smaller is at the top, right. At no other point of time we can have it in, I mean, in such a way that the smaller one is at the bottom and bigger one at the top. So, that is not possible or admissible here. So, this would be some intermediate position during shifting of disks from pole A to C, and this is our expected solution, like we have to shift all the disks from A to C. So, here you could see that first step we shift the n minus 1 disks from pole A to B, and we shift the biggest or the last disk from A to C, and finally we shift all the n minus 1 disks from B to C. So, this is how we find the solution for the towers of Hanoi problem. So, in order to achieve this, what we will be doing is that we will be using the concept of recursion, and so whenever we use the concept of recursion, we will be you know that stacks are getting employed at the background, and we have to deal with activation records. So, of course, the system deals with activation records. So, initially all the disks are stacked on the left pole, we have to transfer all the disks to the right pole, and at a time only one disk can be moved, and a larger disk cannot be placed on top of a smaller disk. These two are the constraints for this problem, and we use the center disk or the center pole in order to hold the disks temporarily while we transfer from left to right pole. So, this is the recursive statement for this towers of Hanoi problem. In the first step, we move the top n minus 1 disks from the left to the center, then we move the largest disk from left to right, and in the step 3 we again do recursive operations to move n minus 1 disks from center to the right. So, here in case step 1 and 3 involve recursive calls to this function. So, this is the code for towers of Hanoi. So, here you could see the base condition. When n is 1, we just print disk 1 is moved from this to this. Otherwise, for all other values of n, we have 2 recursive calls, one call from n minus 1 from aux2. These 3 are the positions dictating poles, and in the last recursive call we shift n minus 1 disks from aux2 and from. So, these 3 denote the start, intermediary and rightmost poles, right. So, these 2 statements, recursive calls, actually involved in shifting n minus 1 disks from first left to middle and then from middle to right. So, here is a very simple case where we have seen 3 disks being moved. We have 3 poles and 3 disks. and those disks have been named as A, B and C, and these are the sequence of moves if we consider just 3 disks. So, imagine that we have the disks named A, B, C stacked one above the other. During the first move, we move disk 1 from pole A to C, and we move disk 2 from pole A to B. So, in our case, you have to imagine that A is the leftmost pole, B is the middle one or the intermediary one, and C is the rightmost pole, and our objective is to move all the disks from A to C, right. So, first is we move disk 1, that is the smallest one, from disk A to C. The second case, we move disk 2 from A to B, that is the second middle one, and the last as a third step, what we do is we move disk 1 from C to B, and then we move disk 3 from A to C. Finally, we move disk 1 from B to A, and disk 2 to from B to C, and finally disk 1 to A to C. So, ultimately, as a result of executing these 3 steps, our entire disks 1 to 3 will get moved from poles A to C. So, to summarize, what we have seen is that we could use stacks in order to manage function calls, especially when we talk of recursive functions. The role of stack is huge, and whenever a function call is made, an associated activation record gets created, and in order to push the activation records onto stack at the time of a call, and to return and to pop the activation record from the stack when we return from a function, the role of stack is exemplary, and that is how with any programming language, wherever functions are in place, stacks play a huge role. And in our case, we have seen how stacks could be employed for handling this towers of Hanoi puzzle, where we move disks from one pole to other, possibly by handling all the moves with the help of stack. So, for testing our understanding of the concepts what we have learned so far, the first question is, how does a stack help manage function calls in recursion? You know very well, whenever a function call is made, activation records have to be created, and with the help of recursion, whenever we talk of recursive function, here the function again and again calls itself, and thereby more and more of activation records will be pushed onto stack, and when the function returns, the corresponding activation records would be popped off from the stack. So, for your understanding sake, here I have given you a question to trace the activation record for Fibonacci sequence. I have given you the sample code and how this activation record for this Fibonacci sequence could look like. So, you can very well try this for Fibonacci sequence, probably having a look at how we solve the example for factorial of the numbers in one of the earlier slides. So, hope you would have understand the concepts of recursion better, and in specific how this works for towers of Hanoi.